Welcome to the presentation of our paper, Efficient Deterministic Distributed Coloring with Small Bandwidth. I am Philipp Bamberger, and this is a joint work with Fabian Kuhn and Yannic. I want to start by introducing the computational models that I will refer to in this talk. The first model is the local model. In this distributed message passing model, the communication network is abstracted by an undirected graph. The nodes of the graph represent processors, each having a unique identifier between 1 and n, and the edges represent bidirectional communication links. Time is divided into synchronous rounds, where in each round, each node can send a message of arbitrary size to each of its neighbors, receives messages from its neighbors, and performs arbitrary internal computations using unlimited memory. At the end of the algorithm, each node needs to know its local part of the solution, for example, its own color in the case of distributed coloring. This especially means that the objective is to solve some graph problem on the communication graph, so the communication network coincides with the problem instance. The time complexity is defined as the number of communication rounds required for the algorithm to terminate. The contrast model is defined in the same way, except that the size of a single message is restricted to O of log n bits. The graph problem we are considering is the delta+1 coloring problem. In this problem, the objective is to assign colors to the nodes such that adjacent nodes have different colors, and such that at most delta+1 different colors are used, where delta is the maximum degree of the graph. Such a coloring exists for any graph, and it can be computed by a simple sequential greedy algorithm. For the distributed time complexity of computing a delta+1 coloring, we know the following upper bounds, solely expressed as a function of number of nodes. For the local and the contrast model, O of log n randomized algorithms are known for more than 30 years. Since very recently, by a breakthrough result of Rojan and Ghaffari, we also know that there's a deterministic polylogarithmic local algorithm for coloring. However, for the contrast model, the best known deterministic algorithm is almost exponentially slower. As the main result of our paper, we give a deterministic polylogarithmic contrast algorithm, closing the exponential gap between the randomized and deterministic complexity of delta+1 coloring in the contrast model. The main building block of our algorithm is an efficient algorithm for a structure called network decomposition. A network decomposition with parameters D and C is a partition of the nodes into C color classes such that the connected components, which we call clusters, of each color class have diameter at most d. So far, this structure was particularly interesting for the local model, because given a network decomposition with parameters d and c, one can solve delta+1 coloring, and in fact many other distributed graph problems, in time O of c times d, by iterating through the color classes and computing a coloring on clusters of the same color in parallel. In the local model, any graph problem can be solved trivially in diameter time by collecting the whole graph topology at one node, solving the problem locally, and broadcasting the solution. At this year's talk, Rojan and Ghaffari presented an algorithm for network decomposition with diameter polylog n, using polylog n colors and taking polylog n rounds in the local model. By the above claim, this proved the existence of a polylogarithmic local algorithm for delta+1 coloring. So how can we make use of a network decomposition in the contrast model? In their paper, Rojan and Ghaffari also provide a polylogarithmic network decomposition algorithm for the contrast model. But it is not obvious how one can exploit a small diameter in contrast. As our main result, We prove that also in congest, one can compute a coloring in essentially diameter time with a polylogarithmic overhead, proving that the delta plus 1 coloring problem can be solved deterministically in polylogarithmic time in the congest model. The improved deterministic complexity also leads to an improved randomized complexity of delta plus 1 coloring in congest. With the log delta randomized graph shattering algorithm by Ghafari, we can color a subset of nodes such that the graph induced by the remaining uncolored nodes has connected components of size O of log n with high probability. Then we run our deterministic polylogarithmic coloring algorithm on these components. We note that this only works due to a recent improvement of the network decomposition algorithm by Ghafari, Kuhn, and Rojon that reduces the dependency of the algorithm on the identifier space. When iterating over the color classes of a network decomposition, and even when running our algorithm within the clusters, we repeatedly color a fraction of the nodes. If a subset of nodes is already colored, and we run our algorithm on the instance defined by the remaining uncolored nodes, this is no longer a delta plus 1 coloring instance, because some colors are now forbidden for certain nodes. Therefore, we need an algorithm for a slightly stronger version of coloring, namely list coloring. In a list coloring instance, we are given a graph with a color list for each node, and the objective is to find a proper coloring of the graph such that each node is colored with a color from its list. Our main theorem then reads as follows. There is a deterministic congest algorithm that solves the list coloring problem for instances where the list size of each node is at least its degree plus 1 in time diameter times log n times log squared delta. Together with the improved network decomposition algorithm, we obtain a deterministic congest algorithm for degree plus 1 list coloring, and hence also for delta plus 1 coloring, with runtime log to the power of 8 of n. For the rest of the talk, I want to give an overview of the proof of our main theorem. We use a de-randomization strategy where we start with a theory-round randomized algorithm that makes good progress in expectation and apply the method of conditional expectation to deterministically fix a random seed that yields a good progress. I will first explain how to apply this technique to the naive approach of just choosing colors uniformly at random for each node. We will see that this process cannot be de-randomized efficiently in congest. But if we slow down the color choice process by fixing colors bit by bit, we obtain a logarithmic overhead in the runtime, but can compute conditional expectations and therefore de-randomize efficiently in the congest model. The arguably most natural randomized algorithm would be to assign each node a tentative color from its list uniformly at random. We define a random variable xv for each node v, which equals the number of conflicts of v, that is, the number of neighbors that chose the same color. We can show that the sum of these values, a random variable that we call x, is smaller than n in expectation. For this property to hold, the color choices only need to be pairwise independent. We can therefore reduce the number of random bits we use because a sequence of n log n pairwise independent random bits, which we need to choose a color for each node, can be generated from O of log n independent random bits, which is desirable because for an efficient de-randomization, we aim to use as few randomness as possible. We introduce a random variable r for each random bit and use the method of conditional expectation to successively fix these bits. This involves the following steps. Assume that the bits up to bit j-1 are already fixed. To fix bit j, each node v computes the expectation of xv conditioned on the already fixed choices and conditioned on setting bit j to 0 or 1. We compute the sum of these conditional expectations, that is, the conditional expectation of the random variable x, via aggregation over a BFS tree. The leader node then chooses the value for bit j that minimizes this conditional expectation and broadcasts this choice. By the law of total expectation, it follows that when choosing the random bits, and therefore a color for each node, in this way, the sum of all conflicts is at most n, which means that at least half of the nodes have at most one neighbor with the same color. So at least a quarter of the nodes can keep their color permanently. Hence, after log n iterations of this process, all nodes are colored. However, there is one obstacle for implementing this procedure efficiently in the congest model. Computing the sum of the conditional expectations via aggregation can be done in diameter time in congest. But to compute the conditional expectations, nodes need to know the color lists of the neighbors, and exchanging color lists is too costly in congest. The idea to circumvent this obstacle is to slow down the color choice. Each color consists of a bit string of length log n. We run log n phases where in each phase we fix one further bit of each node's color. We write SL of v for the prefix of v's color, that is, the sequence of bits of v's color we have fixed so far after phase L. We further write L subscript L of v for the subset of colors in v's list that start with the given prefix. We call these colors the candidate colors of v after phase L, as v will eventually choose a color from this list. At the beginning, each node's prefix equals the empty string, and each color in the list is a candidate color. If we set the first bit to 0, all colors from the list starting with a 1 are deleted. If the second bit is 1, only colors with the prefix 01 remain in the list, and so on. To measure the goodness of the bit choice, we define a potential function, which we try to keep small in the de-randomization. We first define the conflict graph after phase L as the graph on the node set where we only keep edges between nodes that have chosen the same prefix so far and therefore might choose the same color eventually. We then define the potential of a node V after phase L as its degree in the conflict graph, that is, the number of neighbors with the same prefix, divided by the number of its candidate colors. At the beginning, each node's potential is smaller than 1, because it has at least degree plus 1 colors in its list, and therefore the sum of all potentials is smaller than n. We will give an algorithm to choose the color bits such that the potential does not increase much. Concretely, after choosing all color bits, the sum of all potentials is at most 2n. It follows that at least half of the nodes have a potential of at most 4. When all color bits are chosen, each node has only one candidate color left, so the potential of a node equals the number of neighbors with the same candidate color. Therefore, a constant fraction of the nodes have at most 4 conflicts with the neighbors, which is sufficient to permanently color a constant fraction of the nodes. Next, I want to describe the zero-round randomized algorithm we use to choose the color bits such that the expected increase of the potential is small. Assume that node V has chosen the prefix 01 so far, and that it has the following 5 candidate colors left. Among these colors, there are 3 with a 0 and 2 with a 1 at third position. We choose 0 as next bit with probability 3/5 and 1 with probability 2/5. So we extend the prefix by 0 with a probability that equals the fraction of candidate colors having a 0 at this position. Iterating this process log n times yields for each color in V's initial list the same probability to be chosen. So we can consider this as a slowed down version of choosing a color from the list uniformly at random. One can show that when extending the color prefixes this way, the potential does not increase in expectation, even if the choices of the color bits are only pairwise independent. And we are able to use the method of conditional expectation to deterministically fix one color bit. The advantage of this slowed down color choice is that a node does not need to know the whole color lists, but much fewer information from its neighbors in order to compute the conditional expectation of its potential. Concretely, a node needs to know for each of its neighbors the fraction of candidate colors having a 0 at position L. And this information can be exchanged in one congest round. However, there is still a point that needs to be considered. As we aim to use a shared random seed of length log n, the coins we produce to decide on the next bit cannot represent arbitrary probabilities. This leads to a slack in the increase of the potential, which we can upper bound by n over log n. As we have seen before, initially the sum of all potentials is at most n. And after log n iterations, that is, after fixing all color bits, the sum of all potentials increase at most by n. And a constant number of nodes can keep their color permanently. For the whole coloring process, we therefore obtain the following runtime. To de-randomize a single bit of the random seed, we need diameter time. The seed has length log n, so for fixing one color bit, we need diameter times log n rounds. If C is the size of the color space from which the colors in the lists are taken, the colors consist of log C bits, so we need to multiply with log C to obtain the time for coloring each node tentatively. As we have seen, a constant fraction of the nodes can keep their color permanently after this process. So we need log n iterations of this process to permanently color all nodes. With a little more care, we can reduce the length of the random seed to log delta. And usually, as in the delta plus 1 coloring problem, we only consider colors with log delta bits. So we can reduce 2 of the factors to log delta. We can also apply our techniques to the congested click and massively parallel computation model, where we obtain the following deterministic complexities for delta plus 1 list coloring. In the congested click model, we have complexity O of log delta times log delta. And in the MPC model, we have log squared delta for the linear memory regime and log squared delta plus log n for the sublinear regime.